I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for the do.
All right, guys, let's get started. Round of applause for DJ Cash. Awesome. Welcome back.
Thank you.
How'd it go last week?
It could have been a little better. They're saying I have to pay taxes on my beats, so.
Your tax accountant said you pay taxes on your beats.
Yeah.
Well, I mean, not paying taxes on the beats, you're paying taxes on the money you made with your beats.
Right.
Yeah. You got to do that. All right. Yeah. Pay your taxes. All right. But it's good, again, you're getting back where you need to be in life. All right, guys, a lot to cover. And today's lecture is awesome because it's transactions and I get very excited. So let's jump into this. All right. For you guys in the class, Project 3 is coming up this Sunday. That's due. And we have the special office hours. That should be the 15th, not the 5th. I'm missing a 1, sorry. Coming up on the 15th, this Saturday, from 3 to 5 p.m. in Gates. And again, post on Piazza, if you have questions or come to office hours. And then I messed up the due date for homework 5. That was also due the 16th, this Sunday coming up. That's been pushed out a week, and that'll be due on the 23rd. And grades go on Piazza, and the website should be updated for that. Any questions about Project 3? Who here has not started Project 3? Okay. And then I'll post this on Piazza too. If you are concerned about your buffer pool manager or from Project 1 or your B+ tree from Project 2 not being completely thread safe, just put a latch in front of it. Right? Put a global latch in front of the entire page table. And, what's that? Yeah, but like the things that'll slow you down for Project 3 will be like transactional, like the lock manager stuff, not like the page table latch, right? Other questions or comments about Project 3? All right, and then for database talks, after this class today, we have the co-founder from Mooncake. It was a database startup that had extensions for Postgres that could read iceberg tables. That's been, they got acquired by Databricks. So that guy's giving a talk. Tomorrow, as I posted on Piazza, we're having one of the co-founders of DBT flying in from Philadelphia. So he's giving a talk at noon on the 8th floor in Gates, and there'll be pizza at that. And then there'll be an info session for hiring and internships with him at 2:30, also in 8115. And I post that on Piazza. Again, you know the RSVP for that, just show up, talk to the guy. And then the Firebolt guy is Ben, who gave a talk with us on Wednesday. I said he was giving a talk today. I was wrong. It's Mooncake. But he's coming back to give a talk in the seminar series a week from today. Again, that'll be on Zoom. Okay? All right. So last class, we talked about concurrency protocols. And in particular, we talked about two-phase locking. We said this was a protocol that data systems can use at runtime to allow it to schedule the behavior or the ordering of transactions in such a way that you can guarantee serializability, right? And we said this was a pessimistic protocol where the data systems assumes that transactions are going to have conflicts. Therefore, it requires them to acquire locks in different modes on the objects that they were going to access before they're allowed to access them, right? And we showed different variations of two-phase locking, right? And in most systems, they're going to implement the strong strict one where you just end up holding all the locks to the very end. So in the two-phase locking protocol, as I was saying, it's a pessimistic approach. Again, so you're going to assume transactions are going to conflict. But if you assume that they're not going to conflict and that most of the transactions are not going to interfere with each other, and most of your transactions are going to be pretty fast, pretty quick. Right? Think of like loading a web page. That's basically a transaction. Like you're going to get some queries, get a small amount of data, and then you're done real quickly, like in the order of milliseconds. Right? It's rare that transactions will take more than a second on modern systems, right? Or minutes or hours, days, worst case, weeks, right? They were more common in the old days. Sometimes they're common because you have to do like big bulk updates, but most of the transactions don't look like that. The majority of the transactions that are executed in the world are going to be pretty fast. So therefore, if you assume these properties about transactions, you assume that they're not going to conflict, and you assume they're going to be pretty fast, then an alternative protocol might be to not require them to acquire locks, let them do whatever they want to do, and then at the end, when they go to commit, figure out whether there was actually a conflict. Again, because you assume most of the times there won't be, and therefore you'll be faster off than you would have been in a pessimistic approach like two-phase locking. Sound plausible? So that's what today is about. Today is about optimistic concurrency protocols, and these are sort of fall under the umbrella of what I call timestamp ordering concurrency protocols. And the idea is that rather than using locks to enforce the ordering of the operations within transactions, we're going to use timestamps to keep track of the order in which these things occur, or should occur. And then when transactions go to commit, we need to make sure that we generate timestamps for these transactions, or the operations are ordered in some kind of timestamp sequence in such a way that it's equivalent to executing the transactions in serial order, right? Where you have TI and TJ. TI is going to execute all its operations first, followed by TJ. But again, when there's concurrency protocols, I can actually interleave their operations where they don't actually have to physically occur, immediately one after another. They can actually be intertwined. So the way we're going to make this work is that we're now going to maintain these timestamps for not only the transactions as they're actually doing operations in the database system. We're actually, within the database, we're also going to maintain timestamps for the database objects that are in our database. And again, we're being vague here. We're not saying whether it's a tuple or a page or a table or a database. It doesn't matter. The protocol still works. But now we're going to keep track of the timestamps for every single object in our database. When were they accessed? When were they modified? Who was the last transaction? At what timestamp they modified? We're going to maintain all that internally. We'll see next class how we actually can, in some systems, we can, in SQL, we can see these things. In the case of Postgres, it'll expose it to you, but it's not, so it's maintaining this information for you, but it's not always, they don't show it normally when you see queries, because you at the end of the day, the application programmer should know about these timestamps. But underneath the covers, we're going to use them to keep track of things. Remember in the beginning semester we talked about how pages have headers and tuples have headers. Right? This is in that header. That's where we're going to start storing these timestamps. All right. So now the question is be, all right, how do we generate timestamps? They're saying satellites. Two systems do that, but we'll get there. But when you say satellite, what is the satellite giving you? But what kind of time? Wall clock, right? All right, so we're getting ahead of ourselves. So for a given transaction TI, we're going to say that it's going to be assigned a unique fixed timestamp where those timestamp domain is always increasing in value, meaning you can never have a transaction show up in the future that has a timestamp that's less than one that executed before. You have to deal with wraparound when the number gets really big, but if you use a 64-bit integer, then it's going to take a while. And so the different protocols that are out there will assign these timestamps to transactions at different time or different points of their execution. So the protocol we're going to talk about today, you're not going to get a timestamp till you actually commit at the end. You don't get one at the beginning. In the case of something like Postgres, the way they do concurrency protocol, their concurrency protocol, which we'll discuss next class, you're actually going to get two timestamps. One at the beginning, one at the end. Right? But for today's class, we'll assume we'll just have one timestamp. So they were jumping ahead a little bit and saying we can get this, we can get these timestamps from satellites. But again, what you're really getting is what I call a system clock or a wall clock, an actual physical time that's we keep track of as humans. And typically you want to use UTC because you're not worried about daylight savings. Right? You don't want to have the clock roll back and now your timestamps are now in the past. That's going to mess everything up. Right? So daylight savings screws things up, and you want to use UTC. Doesn't have to be coming from the wall clock. Getting from a satellite, GPS satellites, or getting it from an atomic clock. We'll see that later when we talk about Google Spanner. That gives you really accurate timestamps. But there's only two systems that use that kind of thing. DSQL from Amazon that just came out. And the guy gave a talk last class. There's the advanced database class happening at the same time as this class. The DSQL guy gave a talk and it's on YouTube. I'll post something else about this. Right? It could just be also a logical counter. Right? You could just say, increment a counter by 1, and every time a new transaction comes along, you just add 1 to it. Right? Problem with that one, we'll see this when we talk about distributed systems. Like how do you make sure that like your counter is in sync with another node's counter? You can't. Right? So typically, sometimes you can do a hybrid of these things. All right. But in general, for our purposes here today, just assume that there's timestamps, assume that they're unique, and assume that they're always increasing in time, and that we're never going to go, magically back in time with these things. In Postgres, by default, their timestamps are 32-bit integers, so you wrap around eventually, and that causes problems. So we'll talk about this next class, how you handle this, but like Postgres explicitly has to deal with like the 32-bit number wrapping around, and now you have a bunch of timestamps that are in the past, even though logically they're in the past, but physically they're in the future. And this idea of logical time, physical time will come up today. All right, so again, today we're gonna talk about optimistic concurrent serial protocol, which is the primary protocol, the most common protocol people use in a timestamp ordering database system. And again, the confusing part about this is that the protocol's name is the optimistic concurrent serial protocol. It is in the category of optimistic concurrent serial protocols. But you just say OCC and everyone will know what you're talking about. And then we'll talk about at the end how we're going to handle additional anomalies that we're not going to be able to handle out of the box, at least so far what we talked about in two-phase locking and OCC, and how some systems might be okay with these additional anomalies, and we can run at lower isolation levels to get better performance. Okay? All right, so the original optimistic concurrent serial protocol that was based on timestamps, it's called OCC, and the basic idea is that when transactions run, the database system is going to create a private workspace for them, like a little area in memory where they're going to store all the things that they read and write from the database. So anytime I'm going to read something in the database, I'm going to make a copy of it first in the sort of a global database that all the transactions can read from, and I'm going to copy it into my private workspace. And therefore, I can make changes in that private workspace, and no other transaction can see those changes. And then when it comes time to commit, now we have to go look at the other transactions that either have run in the past or are running right now, depending how we want to do this. And we have to see whether they have read or written to anything that we have potentially modified or read in our private workspace. And again, depending on the way we're going to do this validation step, we will we'll end up maybe be allowed to commit, or we may have to kill ourselves and retry. But the key idea is that this private workspace part is where we can do all our changes in like a private scratch space, and no one can see them. So two-phase locking was invented at IBM in 1976 at IBM, working in System R. OCC was invented in 1981 here at CMU. The inventor, H.T. Kung, he's not a database person. He was a networking person. But he came up with this protocol for interacting with databases, right? And I think it's a very famous paper written by a non-database person. Of course, at the end of the day, what do you need a network for? To talk to a database, right? So it makes sense that they were looking at these things, right? The whole point of a network is so you can talk to databases. All right, so the protocol is going to have three phases. And again, because he's a networking person, the names of the phases might be a little weird, but just bear with me. So in the first phase, it's called the read phase. And despite the name read, you actually can do reads and writes. But this is where the data system creates the private workspace at the beginning for this transaction, and anything that it writes will have to be stored in this private workspace. Anything that it reads, you don't have to copy it into your private workspace. But if you want to guarantee that you have repeatable reads, meaning if I read the same thing over and over again, I want to see the same value, then you make a copy into your private workspace. All right, and then when you complete all your read and write operations and the transaction calls commit, then you automatically switch into this validation phase. And this is where the data system is going to figure out, all right, is this transaction allowed to commit? And based on whether it's applying the changes would violate a timestamp ordering that is equivalent to a serial ordering of the transactions. Right, and I'll go through examples of how we're going to do this. And then if you pass the validation phase, now you enter the write phase, where the transaction is allowed to apply its changes that are in its private workspace into the global database. And we're kind of be hand wavy how we're going to do this write phase, but obviously you want this to be atomic because you want all your changes to appear once. So one way to do that is put a global lock on the entire thing. But for simplicity, we'll do that. But in real systems, you wouldn't do that, right? So then if you pass the validation phase, actually, let's see this. When you enter the validation phase, that's when you get a timestamp. Then if you pass the validation phase, all the objects that you get modified are now assigned a write timestamp for this transaction that it got during the validation phase. So you don't get your timestamp when you start, you get the timestamp when you hit the validation phase. And then if you succeed that, then you're allowed to go update the global database with the timestamp you got during the in the commit process. So the read phase, which we'll focus on first, this is basically where all the work happens for the transaction. Then everything else is the commit protocol, that you're making sure that things are allowed to happen, or things will happen in the order that it should happen, that's equivalent to a serial ordering. All right, so let's look at the schedule now. We have two transactions, T1 and T2. T1 is going to read on A, write on A, then read A again. And T2 is just going to do a read on A. And so I'm showing the boundaries here for the three phases, read, validate, and write. Again, just like in the lock and unlock stuff in two-phase locking, you don't explicitly call this in your application code. I'm just showing you the boxes to say where the boundaries are for these phases. So when and so also too now in our database, now we have it's a key value pair, so an object and a value, like A, and the value is 1, 2, 3. And then we have this write timestamp that corresponds to the last committed transaction that wrote that value. In this case here, assume there was another transaction T0 that got timestamp 0, and therefore the write timestamp for this object in the database is 0. And again, we have the three phases here. All right, so our transaction T1 starts. All right, as soon as we call begin, we enter the read phase, and then we create this private workspace that has nothing in it right now. Then when it wants to read object A, assuming we're going to copy everything to our workspace because we want to have repeatable reads, it's going to copy the current value of A, the entire tuple, and put it into our private workspace. Now there's a context switch, T2 starts running. So again, it enters the read phase, we create the workspace for it, and then when it reads A, again, we copy the latest version, or we copy A from the global workspace into the in the global database into its workspace. Then now it goes to commit. So now we enter the validation phase. So this is when, the data system assigns timestamp to the transaction. So T2 is committing first, so it's going to get timestamp 1. So now we're going to run this validation protocol to see whether this thing has read or written to anything else that any other active transaction could have modified or also read. In this case here, T2 read A, T1 read A, but hasn't written to it yet. So therefore, there's no conflict, and T2 is allowed to commit. So when we enter the write phase, there's nothing for us to do because there's no modifications in the private workspace. So we just blow it away and we're done. And now we context switch back over to T1. T1 does a write on A. So in this case here, we're going to update in our private workspace with the new value, but now we're going to set the write timestamp to infinity, just to say that this is something that we've modified, but we don't have a timestamp yet because we don't get one for our transactions until we enter the validate phase. So then now it reads A, and again, you can go read the same record that it modified in its private workspace. So again, that guarantees repeatable reads. Then now it enters the validation phase. It's assigned timestamp T2. Check to see whether there's any conflicts. There isn't because there's no other active transactions. So now when it enters the write phase, it then applies the timestamp it was given to it in the validation phase into its private workspace for the object that it modified. So it got timestamp 2, so now it sets write timestamp to this object in the private workspace to 2, and then it pushes the change up into the global database. Yes? The question is, why is the timestamp assigned at the validation phase after you've done everything rather than when the transaction started? Because you don't know that you don't know what the logical ordering should be before all the transactions finish. So in this case here, T1 started before T2 did, right? So physically, T1 started before T2, but T2 logically committed before T1 does. So therefore, it has a lower timestamp. So getting it at the beginning doesn't make a difference here. Getting it at the beginning would restrain you to make sure that the ordering of the operations for the transactions match the timestamps you were given when they show up. And that limits parallelism. What's that? The statement is, because we assign it when they validate, that it gives us more flexibility to get better parallelism? Yes. Other questions? All right, so this is obviously a simple example, but again, this re-emphasizing the same point I was just making, that like physically T1 started before T2 did, but logically T2 committed before T1 did. That's why T2 has a timestamp in the past from T1. And it makes sense, right? Because T1 wrote to A, it wrote to A after T2 committed, right? If T2 would have committed after T1 did, then it should have seen that write on A, but it didn't. Again, that's why getting the timestamp later rather than the beginning ensures you can, allows you to get that allows you to order the things in a way that's still correct. Even though it's not the same order in which they arrived, but it is still equivalent to a serial ordering. And as we said last class, or 2 classes ago, that's correct. That's our metric for correctness.
Are we able to deal with the memory overhead because we're assuming that these don't usually conflict with each other? Like the transaction usually read different things and the tuples don't require a lot of copies.
So the question is this protocol going to handle the memory overhead of having to make all these extra copies? I mean, if you have to update a billion things, then you have to update it, to make a billion copies in this protocol. We'll see next class in MVCC where you can basically take diffs of the changes you make, and those will be much smaller. But again, I can back all my intermediate results in my buffer pool, and if they get swapped out to disk, that's okay, because I can always bring them back in. Yes?
How do you do the right thing atomically?
The question is, how do you make sure this is happening atomically? So like, I'm showing one tuple getting written. I can do that pretty easily atomically. What do I have to update? Multiple tables, multiple pages. We'll come to that in a second. The original protocol from 1981 just had a single latch, a single lock in front of everything, right? I think so, yes. Yes, for all of them. Because again, think back then, there wasn't, you had one core on your CPU, so it's not like you had a bunch of threads active. There's other tricks, a way to get around that, but it'll make more sense when we do MCC, but I'll talk a little about it in a second. Yeah. There's other tricks you can do, like you can make sure that when you do the validation, if you have multiple workers doing validation in the same phase, that they're all going in the same lexicographical ordering of the keys. So if I updated key A, B, C, and you updated key A, B, C, then I'm going to check A, then B, then C, and you'll go in the same order. So that way, like, you're not checking B and you need to check A, and I'm checking A. Yes. Yes. The statement is you need a fairness guarantee. Yes. That's outside the scope of what we're talking about here today. All right. So the read phase is repeating what I already said. All right. So we're going to track the read-write set of all the transactions. And anytime they want to modify something, again, we're not doing inserts and deletes. We're just doing updates right now. Anytime I want to update something, I'm going to do it in my private workspace. And so if I want to have readable reads, I want to make sure that I copy everything I'm going to read also in my private workspace as well. So that way that when I go read it again, I'm guaranteed to see the same thing. We'll see multi-version control next class. This is where having 2 timestamps can help you, because now you can say not only the timestamp of was this thing modified since I started, and then if it was, what's the timestamp of when it was last considered the latest version, so I can figure out where I land in my ranges. Again, I'm jumping ahead of myself, but that's where the 2 timestamps helps those things. The other thing I haven't talked about also too is, like, in here I'm just showing, all right, it's a bunch of boxes in PowerPoint. Obviously in a real system you have indexes. So how do I make sure that if I'm updating something and I'm going to go read it again, I can do this efficiently? And because if I go check the global index for this table, it's going to point to the database at the top, not to my private workspace. So a little extra metadata I got to keep track of, like, okay, if I'm looking for A on this table, I actually have a copy of it. Don't check the B plus tree. But we can ignore that for now. All right, so the real magic happens with the validation phase. Right? This is how we're going to enforce that the ordering of the operations within our transactions end up matching or equivalent to a serial ordering, right? And so related to what they brought up, in the original protocol, it was all serial validation, meaning like I can only have one transaction in the validation phase at any given time. If I now have to have multiple transactions validating, it becomes more tricky, because if there's potential deadlock issues, I'm taking latches on these write sets and read-write sets of the different private workspaces. It starts to get expensive, but the overall high-level protocol doesn't change. It's just I need more machinery to make sure that I don't have race conditions and other problems. All right, so there's two ways to do validation. And if your system's going to implement OCC, you do one of these two. And at a high level, they're the same, right? In the end, you're checking to see, for each transaction, you're trying to see, am I allowed to commit? And the question is, are you looking back in time or forward in time to see whether you potentially have a conflict? So with forward validation, the idea is that you're going to check to see whether the transaction that's trying to commit, whether your read-write set has a conflict with any other active transaction running in the system right now. Because you can peek in their read-write sets, you know what things they're looking at. You see, have I modified something that some transaction has read, and I'm trying to commit now, and I'm going to be in the past where that other transaction is going to be in the future, and it's going to miss my write. And then again, that would violate serial ordering. Backward validation is where you go to see whether there's a read or write that was made by a transaction that has already committed in the past, and that you missed it. Like you didn't read their changes. And therefore, again, that would violate the serial ordering because now you're traveling back in time and seeing the state of the database as it was before that other transaction committed, and you missed that read. So the second one is the most common one, right? Any system that's implementing OCC, including the DSQL stuff that we just mentioned from Amazon, and a couple other famous systems, they're going to be doing this, the second approach, because it's easier. Because I just go check to see what's the read-write set of any transaction in the last certain time range or something, or I check the timestamp of the latest version of the transaction and see whether it's in the future from when I read it, and therefore I would know I have a conflict. But I want to go through forward validation just because that'll, again, it really clearly shows you the idea of things may physically happen in different order in which may physically happen in a different order than the logical way we want to store this in the database. All right, so as we already said, when a transaction enters the validation phase, the database system is going to assign it a timestamp. And those timestamps are always going forward, increasing in time. And then now we're going to check for the transaction that's trying to commit in the validation phase, we're going to check the read-write set of all the other active transactions in the system. Again, for simplicity, assume they are just in the read phase, right? They're not in the validation phase. In the validation phase, again, you do the same check. But for simplicity, we'll keep them separate. So we're going to say that the timestamp for our transaction, if it's less than any other transaction that's still running, which again, if you don't have a timestamp, then it's infinity. So you're definitely less than them. Then one of the three following conditions must hold in order for you to pass the validation phase and say your transaction is allowed to commit. So the first one's pretty easy to understand. So say you're T1 wants to commit. And so the first check has to be if my timestamp is less than the other transaction's timestamp, and again, if it hasn't been assigned one, it's infinity, then if my transaction is going to complete its validation phase before the other transaction has even started, then it's safe for me to go ahead and commit. So T1 starts, does whatever changes, makes whatever changes it wants in the validation phase, then it hits the in the read phase, then it hits the validation phase, and T2 hasn't started at all, so it can't possibly conflict because T2 hasn't read anything in the database, it just hasn't started. So it hasn't, if I make a bunch of changes, it'll see it, the second transaction will see it when it starts. So this one's pretty obvious, right? Basically saying it guarantees, it's a serial ordering. I would say also too, for this one, I'm showing two transactions. If you had hundreds of transactions, again, if the read-write set is empty, they haven't done anything, then this is trivial to do too as well. All right, the next more complicated one is if, again, T1 wants to commit, if T1 is going to complete its write phase before T2 starts its write phase, and T1 doesn't modify anything that's been read by T2, then there's no conflict and it's safe to commit T1. Another way to think about it is like T1 makes a bunch of changes, T2 read a bunch of stuff. If I take the intersection of those two sets, if it's the empty set, then I know there's no conflict. Right? And what this is doing, this is preventing a transaction in the future from reading an older version of an object that we modified. Yes? the question is, why are we not looking at the right set? That's case 3. So we're building up. So simple one is like, you haven't started running yet, no conflict. This one is you have started running yet, but you didn't read anything that I wrote to, so no conflict. Third one, we'll handle the right conflicts. Right, okay, so T1 starts, right? We create the workspace, it does a read on A, copy that on our workspace, does a write on A, right? We update that in our workspace. Then now T2 starts running, and it does the read on A. And then, so now when T1 wants to go commit, we're gonna check the write set of T1 with the read set of T2. In this case here, we have a conflict because T2 read the object with timestamp 0, but now we're trying to write a new version of it at a future timestamp that's going to be greater than 0. So if T2 was really being executed in serial ordering, where it would execute after T1 committed, then it would have read whatever the version is. I don't use the word version, but it would have read the value at the timestamp that T1 was going to install. But it hasn't, right? So therefore, T1 has to abort. Even though T2 hasn't touched anything, so it's not a write conflict, right? But it read something it read something in the past that it shouldn't have seen because it should be executing in the future. The question is, why not kill T2? T2 didn't do anything wrong. It's your fault, right? Wait, say it again? So his comment is like, T1 did a bunch of stuff. T2 barely has done anything yet. Isn't it better to would it be better to kill T2, and instead of rolling back the changes to T1? Would that still be correct? I mean, for serial ordering, you could play that game. When you start doing parallel ones, then you and I conflict, and now we need to coordinate who's going to die, right? It's just easier to kill yourself. It's like the latching stuff with the B-list tree.
How do you decide? You said that if it was serial ordering, then T2 will occur after T1, and in this case, the timestamp T1 has a greater timestamp than T2, and hence there's a conflict. How do you decide that in serial ordering T2 has to happen after T1?
All right, the statement is, in my example here, I said that the ordering of the transactions has to be one where if T1 has a lower timestamp than T2, then that's the serial ordering. But in my example here, where my black arrow is, think of the black arrow as like the program counter. T2 does not have a timestamp yet. It's infinity, right? So at this point here, T1 is going to get timestamp 1, and 1 is less than infinity, so T1 occurs logically before T2 does. We're at the moment where I'm pointing at the black arrow is.
So what's the benefit of using timestamp and not just compare value and CMU ordering?
The question is, what's the benefit of using timestamps versus what? Using values?
Using value and they're not the same.
Yeah, so their statement is, why even bother just looking at these timestamps rather than just comparing the values and seeing that they're not the same? Because the value, like comparing timestamps is cheap. You know, 2 64-bit integers, that's a single instruction. If I have these huge strings, I got to do diffs on them? No way. Yes?
Can you like live log?
Can you what, sorry?
Live log.
Live lock, in this case?
Okay, keep on aborted and then the application says, okay, retry.
Oh. Yeah.
Keeps retrying.
Yes, so their statement, and they are correct, that in a highly contentious system where there's a lot of conflicts, you may end up just burning a bunch of cycles trying to do a bunch of work on transactions and then only find out that you don't commit. You're not going to be able to commit till the end. So you did a bunch of wasted work. Absolutely, yes. You could do that. So in that case, the pessimistic protocol of two-phase locking would be better. So this work, we've done some research about 10 years ago. We basically tried every single contributed protocol at like extreme scale, like 10,000 or 1,000 cores. And in the end, if everyone's trying to update the same key, it's all the same. Like you get one transaction at a time, right? It basically becomes a serial ordering. So if you have light contention, this will be better than two-phase locking. A little bit more contention, two-phase locking will be better. But then extreme contention, they're all the same. So now there are some academic systems that try to be clever and say, to try to measure how much contention you have and can dynamically switch or adapt what concurrency protocol they're using. They switch OCC or two-phase locking based on the workload. No real system implements that because it's so hard to do one of these. Now I got to do two of them? No way. Yeah, no one's gonna touch that from an engineering perspective. All right, so again, with forward validation, we want to make sure, the basic idea is that we want to make sure that transactions don't miss changes that they should have seen if we were following along in the proper serial ordering. Right, so T2, when it committed, should have seen the update that T1 did, right? But it missed it because it read the global database before T1 installed the change in the global database. Therefore, T1 is not allowed to commit. So an easy fix for this would be just changing the schedule. T1 starts, right? Does a read on A, write on A. That all goes into the private workspace. Then now T2 is going to start, does the read on A. Then it enters the validation phase. So again, at this point here, even though it's the same workload, just the order in which they're doing validation has now changed, right? So the same operations, right? But physically they're occurring the same way, but logically the validation for T2 is occurring before the validation for T1. So T2 checks, have I read anything that that has been modified by any other transaction? Again, we're only checking for whether I modified something that somebody else read, not whether I read something that somebody else modified. Or sorry, that I read something, I did not read something that somebody else modified. So again, T2 is occurring logically in the past. So it's allowed to read the older version of A and allowed to commit. Then now when T1 does its commit, the validation, it's allowed to commit because logically the update to object A is occurring after T2 had committed. So physically the update happened before, but it was in the private workspace that nobody could see. But then now when I go to commit, when I install it, it's okay to happen, it's allowed to happen because T2 was in the past and wouldn't have seen my change. All right, the last one is the dealing with the write complex and the write read complex that they were mentioning. So again, it's basically the same logic. Again, we check to see whether the intersection of our write set with the write set of the other transaction and the read set, if those are all empty, then I know that we have not modified anything that they have written to or they have read. So going back here again, so say now T1 wants to do a read on A and a write on A. T2 wants to do a read on A read on B and read on A. So in this case here, when T1 goes to commit, we'll give it timestamp 1, right? We go update its the right timestamp for its private workspace. Because T2 has not physically read A yet, then there's no conflict allowing T1 to commit. So there's no conflict between the write set here with the read set on this, because this is read B, this is only written to A. So T1 is allowed to commit. We install that change now in the private workspace. Then now when T2 starts running again and it reads A, it's going to read the newest version of A that was modified by T1. And again, and this is equivalent to the transactions executing in serial ordering. So it's given timestamp 2, right? And we didn't do any write, so there's nothing to install. So we just blow it all away. Make sense? So at a high level, again, what forward validation is basically doing is you're checking to see whether your write set conflicts with any other transaction that is still actively running, even if that transaction had started before you did. But if they're still in the read phase, they haven't started the validation set yet, then logically they're going to be in the future of you, even though physically they started before you did. So say again, T1 is the one that wants to commit. So we care about at this point here in the timeline, the validation scope is at the moment that we committed, going back in time all the way back to whatever transaction to any transaction that is still active. So you got to keep around the rewrite set of every transaction. So T3 started physically before T1 did, but we can go back in time and look what T3 actually read. Backward validation, which is we're saying the more common one, this one's easier to implement, and there's less interference with other transactions running at the same time as you, because you're not checking the rewrite sets of transactions that are trying to modify their own rewrite sets. You're just going back and looking what are the other transactions that I've committed that were at least active when I started and committed before I committed. So again, the validation scope for that one, it would be this range here just for T2. Yes.
I have a question for validation.
Yes.
I'm trying to wrap my mind around like to guarantee that when you like let's say in your previous slide, to guarantee that when T2 ends its validation phase, no one else started reading something that T2 wrote. Like to me, to implement that, you kind of need a like stop the world scenario, because like what if you compare yourself with all the other pending transactions, and then while you're at the end of the list, someone at the beginning of the list, like a new one come in or something. Like don't you have to basically stop the world to guarantee that at the end of your validation phase, there's not a new start?
Right. So their statement is, and they are correct, that mostly correct. Like, don't I need to make sure that when a transaction goes to validate, that so you're talking about the validation or the write phase? What part? Like, have I gotten past validation yet?
Validation, the moment where you make sure that no one else started reading something that you're writing.
Yes. So if you do serial validation, yes, simplest way is you stop the world, right? Or that you could put hints up and say, I'm in the global database or in a posting table somewhere that says, I'm trying to validate now. Here's the things that I've modified. So I'm going to go check to see whether anybody else interferes with me. But anybody else that tries to read this, the thing I'm trying to validate on, wait.
So it's also a little bit backward. Like there's a backward component. Because like when a new transaction comes in, you need to read this data structure that you just described.
Their statement is correct that like there's a little bit of backward validation being done by transactions when they start, because you have to check to see whether this thing is in the process of being committed. Yes. But that's what I'm saying. So if you assume the transactions are fast and the rewrite sets are small, then like there's a window, yes, but it's going to be fraction of a millisecond, less than a millisecond, because you're just checking things in memory. But again, if my transaction ran for hours or days, then yeah, that's going to be basically locking the whole stuff down to be a single thread executing. Absolutely, yes. It's unavoidable. MVCC will handle a little bit of that, because they'll do basically they'll store in the tuple itself the metadata about what's being committed or not. You still have to check. There's an active transaction table to keep track of, like, here's all the transactions that are still running. You got to go look at them. But like, you don't have to check like I can get information about whether the current version of the object I'm looking at is the one I should be reading directly by looking at the object, but without checking a global thing. But that'll be next class. Yes.
So in backward validation, the validation step, we have to check everything that has committed, that was active when we started. Do we like keep a set of everything that's active when we started?
Yeah. So the question is, with backward validation, I said you have to check all of the transactions that have committed, that committed since I started. Yes. So there would be a transaction table we'll cover next class. There's a basic internal table that says, here's all the transactions that are in some state in my system. And they could either be like waiting to start, running, like in my read phase, validation phase, write phase, and then also like committed, but not completely gone, because someone is still depending on a note, maybe depending on to see whether they conflict with them.
Okay, but like in forward validation, once something commits,
Yes, in forward validation, once something commits, and we pass the validation step, then we're done with them. Yes. Yes, I think the answer is yes.
Why can't you just go into the database and check like the main tables? Like there are timestamps associated with all the objects that you wrote to check those timestamps.
So the question is, be very clear when you say check, who's checking and when are they checking?
So when you try to validate,
So
do you need a list of committed transactions instead of just going to the main database and checking the timestamps of the objects that you depended on?
right, yeah, they are correct. So in this step here, why do I think keep track of the transactions that are around? Why did I check the object that I wrote to or read to? You got to check the reads as well. So like, why not check every individual tuple versus just checking this like state table I'm mentioning? Because if for correctness, For correct reasons, what you're proposing is still correct. Like whether you check the state table, the transaction state table, or the individual tuples, it'll still be correct. It's way faster to go check a single state table. It's gonna have all your information because that'll be in memory. Whereas if the tuples that they modified that I read, but I didn't write to, so I read them and maybe they got swapped out the disk. Now I gotta go read them again to see whether someone has modified them since the last time, right? We'll see this in, it sounds like a crazy idea. You're basically trying to say, I got to read it twice. Some systems will actually do that. We'll cover that in this class.
Another question, typically is backward or forward validation faster?
The question is backward validation versus forward validation faster. In the end, I think performance is the same. Engineering-wise, backward is easier. That's why most of the systems do that. Because there's less interference with the runtime of other transactions. With backward, I'm just going to see whether things have already committed, they've already done. So I'm not really interfering with them because they're dead, or they've moved on. And most systems implement the backward one. All right, so then this one we covered already about like the serial commits and the parallel commits. Again, it's a bit more complicated. It just you have to make sure things happen in sort of in the same order. And you acquire latches on the various data structures you're using to check different things. We already covered a lot of these points. All right, so the main takeaway from OCC is that this is going to work really great if the number of conflicts are low, right? If all the transactions are read-only, then that's the best situation because who cares whether you and I read the same thing because we did, so we can commit right away, right? But as I've already said before, if you have high contention, you actually do have a lot of conflicts, then this is going to perform worse than two-phase locking because in the case of two-phase locking, if I find out I have a deadlock, I'll find out the moment I try to acquire the lock. I won't do a bunch of work and then realize that was a mistake and have to throw all the work away. Now, I may do a bunch of work and then try to get the last lock I need after doing a million things and then get a deadlock and get killed. So you can still have the same problem. But in many cases, because two-phase locking is pessimistic, you can't do things until you get the locks. So if something is high contention, you won't get the lock for it, and you don't end up wasting time. The other thing that we'll see next class, the big problem with OCC is that copying from the private workspace, that sucks. That's a mem copy. That's a terrible thing to do. Right? It's always going to be slow. And in the case of multi-version concurrency control, what we'll see is that you can basically like take a diff of things and only copy the things that you actually modified. And that can be much smaller. Because if I have 1,000 attributes and I only update one of them, and what I'm showing here today, you have to copy all 1,000 attributes into your private workspace. In the case of when we see Delta records and MVCC, I just copy the things that I modified. What's that? The question is, what about non-repeatable reads? Timestamps will fix that for us next class. Yes. So Postgres is basically going to be doing what I'm describing here today. Instead of copying to the private workspace, they're going to copy tuples back into another page in the table. No, they're using, again, this is where things get muddy. They're doing multi-version concurrency control, which is going to look like MVCC, but they're using two-phase locking to protect things. But also predicate locking for serializability. We'll get there in a second. Okay. All right. So any questions about OCC before we jump into more stuff? Because now we're talking about how we handle inserts and deletes. Because this is where everything we've talked about so far is going to break. We still need it, but we need to make it better. So again, if it's just updates, and reads, that's fine because the set of the objects, the number of objects in our database is not, or tables are not going to change. But when we start now having modifications that can affect the result of queries within our transactions, like looking at higher level concepts instead of just reads and writes, then we have to be, then these protocols aren't going to work. So look at two transactions now, where now we're actually going to be doing queries, right? Instead of just doing again, simple reads and writes. But again, the data systems at the end of the day is just going to see reads and writes on objects. But SQL queries is easy to understand. So we have a table of people. We have their ID, a name, and a status. And so T1 is going to start. It's going to run this aggregation query. It's going to count all the people where the status is paid. Then there's a context switch, right? And it gets a value 99. Then there's the context switch over to T2. T2 is going to insert DJ cache into the table and set his status to paid. Good job. right? And then it commits, and again, install our change into the database. Then now, T1 is going to run again, run that exact same query, but now the count of number of people paid is 100. Right? So again, this is an unrepeatable read. But it's not unrepeatable on a single object, it's unrepeatable on a range of objects. Right? So two-phase locking and OCC will have this problem. So what is the problem? Well, assume we're doing 2PL for simplicity. The problem is that you can't acquire a lock on something that doesn't exist. Right? He wasn't in the database or the table at the time the first query ran. So even though it took a shared lock on everything, right? And again, yes, you can take a shared lock on the entire table. Assume it didn't do that. It couldn't take the lock on his record. Therefore, I was allowed to insert a new record with his information. And then I run the same query. And then now I'm seeing things that weren't there before. Right? And again, if we were running in serial ordering of our transactions, we shouldn't have that phenomenon. We shouldn't have that problem. So this is what is called a phantom read. Right? Phantom or ghost, or apparition, whatever. And the idea that tuples are magically going to appear and disappear and cause us to get incorrect results in our queries, that should not happen if you are running in true serial ordering. Right? So range scan is the most obvious way to think about this. It's something I read a range once, I don't see it, there's no value in there, then I read it again, and now there's a value in there that I didn't see before. Or the value that I saw before now has been deleted. Right? Question, how could another transaction delete it if you hold a shared lock on it? Depending on how you're defining the ranges. Keep it simple. Yes. Let's assume that someone inserted something, but the idea is the same. Right? Or again, for two-phase locking, that when I care about OCC, that could still happen. All right. So how can we fix this problem? Yes, question. Their statement is, this phantom problem is because like I'm within one transaction, I'm not seeing the same results. Yes. So like if I run and I get 99 and then you run and you get 100, that's okay. Because again, like that insert should have happened in between my query and your query, right? And that's equivalent to a serial ordering. It's like within one transaction, are things disappearing? Okay, so how can we solve this? There's 4 basic categories approaches, right? So the most obvious thing is just lock everything. Lock the table, lock the database, lock the pages, whatever. And then that way you can't insert anything into into a range that I've read, right? If I lock the entire table, you can't do any modifications, problem solved. But again, if I have a billion tuples in my table and I'm only reading small ranges, that's probably not a good idea because now I'm locking more things than I actually need. Another approach is what sort of we're talking about here, is you just rerun your scan again when you commit and see whether you see things that you shouldn't have seen or things have changed. How would you know? You got to keep track of your read set. They said that that's potentially billions of rows. Yes. Well, we'll come to that in a second. You can do the reverse. The question is, do I keep track of all the billion rows again? Yes. Or some kind of fingerprint of it or something like that. But again, this is what I'm saying. Like if you assume your transactions are small, most transactions are, then this is okay. If I go read your account record once and then read it again, no big deal. Or I read all your orders. Say you bought 10 things on Amazon, you have 10 orders on Amazon, read 10 orders, no big deal. It's not for free, but you have to do it. What's that? Not that expensive, yes. Again, there's no free lunch. And then predicate locking and index locking, we'll cover that in more detail, right? So again, this is what IBM figured out in 1970s, 1976. Like they figured out that the ordering, or trying to figure out how how to do this efficiently, at least in case of predicate locking, is going to be an NP complete problem, or NP hard, right? Re-executing scans, that's easy to do if everything is in memory, everything's fast. But again, larger things are problematic. So the most common of these is going to be the bottom one, index locking. We'll see that in a second. The two middle ones are kind of pretty rare. For re-execute scans, you only see this in in-memory queries. And then the one at the top, lock everything. Again, some systems will do it if you care about serializability. All right, so let's talk about re-execute scans. So again, you basically keep track of all the where clauses for any query you run. And then when a transaction commits, you just check to see whether the output of those where clauses match what you saw when you ran them the first time. So you don't need to, like, if it's a select query that computes that aggregation, I don't need to keep track of the aggregation result or whatever computation I'm doing or the joins. I just need to know for all the base tables, what data did I see, right? So I just run it again and see whether I get the same result. So Hackathon does this. DynamoDB and Fauna kind of do the opposite, reverse it, meaning they run your queries first, but don't make any changes to the database. They call them like reconnaissance transactions. They run your queries and see what it's going to do. Keep track of your scan sets. Then you go to commit, and then you actually run the queries for real and see whether you match what you did when you ran it the first time. If yes, then you know you got things in the right order. So you're still doing the timestamp ordering or the two-phase locking part when the fake transactions run first, or the fake queries run first. And then now that I know that I got the right ordering, if I run them again, if I get the same result, since I scheduled you in a serializable way the first time, then when I run it for real and I get the same result, then I know it's the same. And you're safe to commit. In the back, yes. Wait, so your setup is the first transaction is, you said long? Long in time or long in like they're updating a billion things? Okay, you're updating a billion things, and then you have another transaction that's really short. Yes. 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 All right, so their scenarios, I have transaction T1, it updates a billion things. Transaction T2, while T1 is running, comes in, reads something from that T1 modified, and then it goes ahead and goes to commit, right? That's your setup. If you cared about serial ordering or serializability, T2 is not allowed to commit until T1 commits because it did a dirty read. It read something that T1 modified, and T1 is not committed yet. So if you care about serializability, then you have to wait. If you don't, we'll cover that in a second, then you commit. And then you as the application programmer, deal with whatever the consequences of that, right? Database did what you told it to do. All right, predicate locking, the idea, again, this is what they were proposed to do in IBM in the 1970s. Again, realized it was super hard to do on the hardware they had at the time, and also doing this exactly is again NP hard. The basic idea, the way to think about this is that you're going to maintain this high dimensional space of all the possible locks you could have in your database based on predicates. So not locks on individual tuples like we did in two-phase locking, where like there's a lock table and I acquire a lock on record 1, 2, 3, right? Just think of it, it's a more abstract concept. And then I'm going to check to see whether I have any of these polygons or these high-dimensional objects that are defined based on my predicates. If they intersect, then I know I have a conflict in those transactions. And then I just do two-phase locking or whatever to figure out the order in which things should occur, where you have to wait or kill yourself, or whether I have deadlocks. So again, this is obviously very difficult to do if you have a lot of predicates on a lot of tables. And so you can approximate this using precision locking, where you just look at the read-write sets and you figure out whether there's overlap. So you got to keep those things around. In the case of Postgres and a bunch of other systems, they're gonna approximate this using index locking, which we'll talk about in a second. So no one does this exactly, because again, it's kind of too hard, too difficult to do. But again, you can kind of get away with it using, well, you can get away with this precision locking stuff, which is basically you look at the rewrite sets and you see whether there's conflict. Therefore, you know the predicates overlap. So the only system that does this with precision locking is these German systems, and they're all written by one guy, right? So CWB, Umbra, and Hyper, it's all written by this one guy in Munich. And the precision locking papers, like from 1983, it had like 30 citations when the German guy found it, and it's like, this solves exactly my problem, right? And he implements exactly what they're doing here, and it guarantees serializability. All right, but the original proposal of predicate locking looked like this. So I have my predicates, and my two queries, and I just extract out the where clause. I'm going to map that to some region in this high dimensional space. So for simplicity, I assume that there's only two dimensions. There's a status and the person, right? So then now for this other one here, when I insert this query, that's the same as acquiring a lock on the name, DJ cache, and the status is paid. And then if I know that the two regions overlap, I know that there's a conflict in their predicates, and therefore I have to decide now my protocol who's allowed to acquire the lock and who's allowed to commit it, and so forth. Again, for 2 dimensions, it's easy, but think of like a table of 10,000 columns. This becomes unmaintainable. Yes?
So how does precision locking work again?
Precision locking, we teach this in advanced class on here. The basic gist of it is like you look at the rewrite sets of the transactions.
Like the exact rows?
Yeah, the exact rows, and you just check to see whether like their predicates, whether you're basically running the, how does this? You're taking the where clause of the other query, and you're seeing whether it matches any tuples in the rewrite set of the other transactions. You'll see something. You'll see a watered down version of this in Project 4. Right, but think of like the read-write set is just another table. So I just run my query that I'm going to run in my transaction on that rewrite set and see whether it matches. All right, so most systems are going to do predicate locking, and you can kind of think of this as a special case of index locking, where we're going to use the indexes themselves as the mechanism or the data structure to keep track of what locks are being held by transactions, and this will cover the values that don't exist yet, and allows me to lock them. Because again, I don't want to have if I'm doing two-phase locking, my lock table, I don't want to have entries for ranges or things that don't exist, because that's going to become difficult to maintain and actually build. So I'm going to use indexes themselves, because they're already going to have data in an ordered manner, and I can use them as the way to figure out how to lock things. So there are going to be four different approaches, and we're going to build up and start with the basic ones, like the key value locks, but then we can combine all these together and include the hierarchical locking that we talked about last time to see how we actually implement this in a real system. Yes? The question is, if you have no index on the keys, you have to fall back to scans.
But like, how do you lock them?
How do you what?
How do you lock them?
The question, how would you lock this? You lock the entire table. Yeah. The question is, how do you lock something that doesn't exist? Gap locks. 2 slides. All right. So the most basic one is a key value lock in your index, right? This is where you have a thing that you know it exists, right? And then I can just take a lock on it, right? And again, you don't store this in the actual B+tree node itself. You're going to store this in a lock manager. But now you're keeping track of like within this value, within this index, this transaction holds the lock for it, right? For an exact match. For things like infinity, right? The upper bounds or lower bounds, right? You can just have virtual keys for those, but it works basically the same way, right? So then now, to handle the case they were asking about is, how do I lock things that don't exist? Well, again, say that I have now a transaction that wants to insert value 15, right? Between 14 and 16. 15 doesn't exist yet. So I'm just going to keep track of all the gaps between the keys that I do have in my index. And then now I can take keys on the gaps. Or sorry, take locks on the gaps. So this is going to say, I'm going to have a lock on the gap between 14 and 16 exclusive. So again, these are all integers, but say someone inserts like 15.1, 15.2, 15.3. All of that would be covered by this single gap lock. Right? If it's integers, it's only 15. But for any possible value, the thing is strings, I have key AA and a key ABC. I need a gap between the two of them. And the gap block would handle that. But then now I don't want to have to keep track of maintain a lock for every single key value pair that I want to maintain, and every single possible gaps that I may have within a range of values. So now I start combining them together and take key range locks. So my lock tables, I'll basically keep track of like, here's the starting point, 14 inclusive, and then the key range lock goes up to 16 exclusive. So now if anybody wants to insert something in this range, they got to go acquire the key range lock for this that covers the gap, and it would tell me whether I'm allowed to put something there. So I'm going back to that query I had at the beginning where I'm doing that scan to try to find people within a status, right? I could take the key range lock from that status equals paid up until whatever the next key is, including the gap. And that'll prevent somebody, another transaction from inserting a value in that range. Right? You can go in other directions. Typically, in your system, you only go one direction. You either go to the current key and going backwards in the ordering, or the current key and going forwards. But you only do one. All right, so now we can put this all together and start doing hierarchical locking that we had before. So again, this is kind of different than we talked about before, because we were like, I was taking locks on tuples and tables and so forth, but now I'm taking locks on actual values and actually within the page itself in my B plus tree. Right? So I can take an attention exclusive lock on this sort of range of values within the page, right? And then within inside that, now I can take an exclusive lock on the key range from 14 inclusive to 16 exclusive within the gap. But then also I can take an exclusive lock within another transaction, can take an exclusive lock on another key value pair or key range by taking an attention exclusive lock, which is compatible with the attention exclusive lock that somebody else had maintained. Now I can lock 12. So two transactions can come in. Somebody could be updating 12 and somebody could be updating 14 up to the gap. And this will prevent phantoms for me. Because again, I'm trying to avoid from people inserting something that didn't exist before, because this allows me to take locks on things that I didn't know about before. Okay? Yes? The question is, what does a gap lock look like? What do you mean? Like, the question is, how would you actually implement it? So you just keep track of like, here. You would keep track of like the range in which this is being locked. So 14 exclusive to 16 exclusive. So in the lock table, you would keep track of like that interval. And so therefore, if anybody is trying to read something, they'd be scanning along the leaf nodes and they're finding values. Say you don't know the values that are, or the keys that are in a range before they start. Before you go read something, you have to go check to see whether you can acquire the lock on to read something. So think of like the B plus tree implemented in project 2. You got to go check the lock manager as you're scanning along the leaf nodes. Yes.
So if you come in and you intend to modify a gap, so like add a value, do you always lock everything until the end of the page, because you might be moving the values, right?
The question is, if I intend to insert something into this gap, do I lock from the gap to the end of the page? You would know. Again, at this point, you're inside the page, so you know what the values that are here, right? So you have it in some kind of read mode. You're reading things. That's okay. So then I'm going to go check the lock manager. So I know what I'm trying to insert or delete, right? So you go check the lock manager. Give me the lock for the thing I'm trying to modify. And it may be to the end, or may not be. Depends on what you're trying to do. But I'm saying you'd have to know the value you're trying to modify in order to acquire the lock for it.
Yeah, but let's say you're trying to insert 15.
Yes.
Isn't it true that you're going to move 16 and up? So you need to lock everything on the right.
So his question is, if I insert 15, and then now I got to split this node. How about that, the B plus tree?
That means splitting, just like adding in the middle, so like you push everything.
You're talking about physically within the page? Yeah. I still have to take a write latch on the page. These are logical locks. So I'm trying to lock the logical values that are stored inside the page. In order for me to modify the page, I have to take a physical latch. Does that make sense? So again, so like, in order for me to physically modify the bytes within a page, I have to have a write latch on that page. There's another, this is what we were separating locks and latches. The locks are protecting the logical contents of the database. The logical contents are the keys that are stored within a range. I'm using the index as the mechanism to efficiently keep track of that range. But I still have to maintain all the physical correctness using the latches. Lots of hands, yes.
Does this mean that when you're trying to do a serializable transaction and you don't have an index on a certain key, then it's going to be really inefficient because you are going to lock the whole table?
The question is, does that mean if I'm trying to run serializable transactions where I don't have an index on the ranges that I'm looking at, could that be causing them to be expensive? Yes. It's no free lunch, right? Yes.
Has anyone even tried to do syntactic effective locking where they analyze the predicates that it gives you in comparison with all the other predicates used by?
The question is, has anybody tried to do static analysis of the predicates to see whether you would have conflicts with other? Maybe, but as soon as you have functions inside that thing, it comes. The statement is could you do a quick fix? Could you quickly try to assess whether you can determine statically through the predicates whether you would have a conflict with other transactions? If no, and it's provably correct, then you're good. If yes, then you fall back to the more heavyweight. If you can't verify that they're not going to
Is there any work in space?
The question is there any work in the space? Maybe. It's been 50 years since people are trying to do this, so maybe. I just don't know. Yeah. Questions in the back, sorry. Okay. I think we've covered all this. All right, so now, here's the dirty secret. We spent the last 3 classes talking about how great serializability is, how it's important to keep track of what transactions are doing so you can generate schedules that are serializable. The dirty secret is most databases do not give you serializability by default, right? And in some systems, they'll lie to you. Oracle famously does this. If you say to Oracle, I want serializable transactions, it'll come back and say, yep, got it, no problem. It does not give you serializability. It gives you a lower form of isolation, right? And so the reason why these systems are not going to do all this extra stuff we've been talking about the last 2 classes, they're still going to do two-phase locking, they're still going to do OCC, but all these extra mechanisms I just talked about now to guarantee serializability, they're not going to do these things because they're expensive. They kept asking in the front row, what if you don't have indexes? How do I do this? You have to do the slow thing and just scan everything. And so by default, that's going to suck. If that's on by default, that's going to suck. People are like, yeah, this database sucks. It's so slow. And they're going to switch to something else. And you lose out potential customers. So that's by default, most data systems are going to run with a lower isolation level. So now the question is, what is an isolation level? So an isolation level is going to control the sort of how aggressive you want the data system to be to ensure your transactions don't incur any of the anomalies that we talked about before, right? Dirty reads, unrepeatable reads, loss updates, and then the phantom reads we just mentioned here. So by default serializability, make sure that none of these things happen. But if you run at a lower isolation level, so when a transaction starts, you can tell the system, run my new transaction, but run with a lower isolation level. You may incur some of these other anomalies. And so what I'm showing here is the basic ones that were originally defined in the SQL standard from 1992. And this is assuming you're running in a system that uses two-phase locking. But the highest level is serializable. So you say, I want my transaction on a serializable, and you're guaranteed to have no phantoms, everything's repeatable reads, and then no dirty reads. The next lowest isolation level is called repeatable reads. And this is where phantoms might happen, but the other 3 types of anomalies will definitely not happen. Read committed is that you have phantoms, potentially unrepeated reads, because you're reading data from transactions that have recently committed, but maybe you read it first an object before they committed. So you see the data one way, then they commit, and now you read it again. And because you're allowed to read committed data, you'll see different values. So you may have unrepeatable reads. And the read uncommitted is just like you're driving up the seatbelt. All these anomalies may happen. Now I'm counting my language here. I'm not saying they will happen. I'm saying they might happen. Because again, if I just execute one transaction by itself and no other transactions, that's serializable, right? If one transaction in one schedule with no other transactions is by definition serial. So that's always going to be serializable. So I'm putting a bunch of maybes here just to say that like, if you run at these lower isolation levels, you may have these problems. Depends on whether the other transaction is running at the same time that your transaction is running, is reading and writing the data that you're reading and writing to. So now, if you do this in two-phase locking, how do you actually implement this? Well, again, you just turn off a bunch of the stuff I just spent the last half an hour telling you how to do. Right? Again, OCC basically works the same way. But in the case of two-phase locking, if I run with strong strict 2PL with additional phantom protection by either like re-executing scans, the index locks, or predicate locking or whatever, right? Then I'm guaranteed to not have any phantoms, and all the transactions will run in serial order, or the equivalent to a serial ordering. For repeatable ease, you just don't do the index locks or the stuff we talked about at the end. Just do two-phase locking, strict two-phase locking, strong strict two-phase locking, and you're guaranteed to get everything without everything but phantoms. Recommitted, for this one, you basically just do 2PL. You don't do any index locks or gap locks, the things we talked at the end. And then when a transaction reads an object, you acquire the shared lock on it, and then you immediately give back the shared lock. You release the shared lock. Again, it violates 2PL ordering, but again, you're going to get better parallelism because you can guarantee that other transactions can read data that you've read immediately. You still hold the write locks to commit. And then in read or committed, you just don't take any shared locks at all. If you modify something, again, it's about what you, but what your transaction cares about. So I want to make sure that I don't have any lost updates. So I'll hold the write locks until I know I'm not going to write to that transaction anymore. And in case of most systems, since you can't supposed to call unlock on a exclusive lock on a tuple, you just hold it to the very end that you commit. Same as you cannot have lost updates for read committed and below. You can.
Yeah.
Yes.
So you don't need to hold exclusive locks until the very end. Right?
Yes. So it's hard. If I want to avoid lost updates, I don't want to write something and then not be able to read it. So yes, so you give up the exclusive locks, I think, on a read committed. Let me double check this. Yes. Again, hopefully it makes it clear this is hard. So again, what you define what isolation level you want if you want something other than the default when a transaction starts, right? And different systems have different syntax on how to do this, right? And then the default is going to depend on what your system actually provides for you. So this is just a quick survey of a bunch of various systems that are out there, and you see that there's this little part here right here from SQL Server, MySQL, Oracle, and Postgres. Those are the top 4 relational database systems in the world, right? And by default, none of them give you serializable by default, right? In case of MySQL, MySQL is actually better than the others because it's actually giving you repeatable reads, which is higher than, what's that? All right, the question is, what is snapshot isolation? That's the next class. So when they defined the SQL standard in 1992, they forgot about this multi-versioning stuff we'll talk next class. And there's a anomaly that can occur with snapshot isolation that doesn't occur with two-phase locking. And the isolation level, therefore, is classified as different. It's called snapshot isolation. So it just means that I see a snapshot of the database that was created by any transactions that committed before I started. Yes?
So in the beginning of class, we discussed optimistic concurrency control. Does all database systems have some version of that?
The question is, do all data systems have some version of OCC? No. Some systems will do 2PL, the two-phase locking. It's one or the other. Multi-versioning is going to be, you can do multi-versioning. We'll see next class. You can do it with two-phase locking, or you can do it with OCC. But the way you also do multi-versioning is with timestamps. But like the timestamps will just tell you what version, when was a version created. It doesn't tell you who's allowed to do what and when. OCC or 2PL defines that ordering. Question, which one's the most common? 2PL. Yeah. All right, so, right. We're jumping ahead. Okay, sorry. So synapse isolation we'll cover next class. There's a few systems that do serializable, right? Ingress was what Stoneberger built before Postgres. CoshDB was a distributed system out of New York City. VoltDB is a system I helped build when I was in grad school, right? By default, you get serializability. You can't run anything lower. Google Spanner, and I guess DSQL also as well. I'm not sure about DSQL, but Google Spanner is one of the few systems that support strict serializability, also known as external consistency, meaning the order in which transactions are committed is the order in which they arrive in the system. So they're getting timestamps when they show up, and that's the order that's going to use to determine when they commit. Then he's like, what is cursor stability? So that's this other weird thing. Again, there's a whole bunch of different isolation levels beyond the four basic I told you. And you can sort of think of like this sort of chart here at the bottom, you have read, commit, read uncommitted. I think there's even one below this, but SQL doesn't support this. And so now you have sort of two branches. You have above read committed. You can think of like what you're getting fewer anomalies. Cursor stability is something that IBM DB2 does. Basically, you hold a read lock, a shared lock on the cursor that's reading the data, and that guarantees that within like as the cursor is scanning the data, I'm holding implicitly a lock on that range. But then when I'm done scanning, I give it back up. So as I'm reading the table within my cursor, I'm guaranteed to see a consistent view. But then after that, if I read it again, it won't be repeatable. Yeah, there'll be no inserts or deletes while I'm scanning. Yes, only in the range. Yes, but then as soon as I'm done scanning, the cursor gives it up. Again, and then strict serializability again it's the order in which they arrive. So I'm going fast here. We'll do demos and look at this more in the next class. But the main takeaway I want you to get is like most data systems that are out there today, most workloads are not running with serializable isolation, even though I made a big deal about it, right? So this is a survey we did a few years ago where we asked DBAs for their databases running in production, what's the most common isolation level they're using? And you can see the most common one is recommitted, because that's the default in most systems, right? What's that? Is it a reasonable default? Nobody knows, right? Because it depends. Because again, these problems might occur. So like, if 99.99% of the time, there's no issue, but then there's one time maybe you read something you shouldn't have read, how would you know? Right? Or like you sometimes you see weird things of like, anytime you maybe refresh a website and you don't see counters look correctly, that's eventual consistency issues, not this. But like for other things, like you wouldn't know. All right, I'm blazing all this, so I apologize going fast. But the main takeaway from all this is that there's basically two categories of control protocols: pessimistic, like two-phase locking, and optimistic, using timestamp ordering that we talked about today. Right? There's no one protocol better than another. And then next class, when we talk about multi-versioning, it's actually being a combination of all these techniques put together. And we're going to now, instead of maintaining a private workspace, we're going to have the new versions of change, or the objects that we're modifying, they're going to show up in the global database, and we're going to use these timestamps to figure out what we're allowed to read or not read. Okay? Hit it.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.